Welcome. In this session, we'll tackle the problem find largest value in each tree row. We'll explore how to work with binary trees effectively while identifying the largest value in each row. Let's dive in and uncover the most efficient solutions. In this problem, we are working with a binary tree, and our goal is to find the largest value in each row of the tree. The tree is structured with nodes, where each node has an integer value and pointers to its left and right children, which could be null if the child does not exist. The output of the problem is an array where each element represents the largest value from the corresponding row in the tree, starting from the root at row 0. For instance, consider a tree where the root node has a value of 1, with children 3 and 2. The left subtree of node 3 contains nodes 5 and 3, while the right subtree of node 2 contains a single node with value 9. The task is to traverse this tree row by row, identify the largest value in each row, and return the results in an array. For the given tree, the output array is 1, 3, 9. This is because the root node at row 0 has the only value 1, which is also the largest. In row 1, the values of nodes are 3 and 2, and the larger value is 3. Finally, in row 2, the values are 5, 3, and 9, with 9 being the largest. Another example demonstrates a tree with a root node of value 1, children 2 and 3, and a single leaf node 4 extending from the right child of node 2. Here, the output is 1, 3, 4. Row 0 contains only the root node with value 1, making it the largest. Row 1 has values 2 and 3, with 3 being larger. Row 2 contains the single leaf node with value 4, which is the largest by default. In the simplest case, a tree with just one node, such as a root node with value 1, will result in an output array of 1, since there is only one row, and the sole value in that row is the largest. The problem also comes with constraints and edge cases to consider. For instance, the number of nodes in the tree can go up to 10,000, and node values can range from -2 to the power of 31 up to +2 to the power of 31 minus 1. This means the solution must handle large trees efficiently and work correctly even when node values are negative. Important edge cases include single-node trees, trees where all nodes have the same value, skewed trees with nodes only on one side, and trees where all values are negative. For example, consider a tree where the root node has a value of -10, with children -20 and -30. The right subtree of -30 contains nodes -15 and -25. Here, the output array is -10, -20, -15. In row 0, the root node -10 is the only value, making it the largest. In row 1, the values are -20 and -30, and the larger value is -20. For row 2, the values are -15 and -25, with -15 being the largest. This example highlights how the solution must correctly identify the largest value in each row even when all values are negative, ensuring that the algorithm is robust across a variety of tree configurations and value ranges. To solve the problem of finding the largest value in each tree row, we explored a few different approaches, each with its own intuition and trade-offs. First, the brute force method involves using a recursive depth-first search, or DFS. Here, we traverse the tree level by level, keeping track of the largest value at each depth within a dictionary or list. This approach is straightforward, as the recursive stack helps us naturally explore all nodes. However, while the time complexity is O(n), because we visit each node exactly once, the space complexity depends on the height of the tree, O(h), which could be problematic for deep or skewed trees. Stack overflow can occur when the tree height becomes very large. On the other hand, an optimized approach involves an iterative breadth-first search, or BFS. This method processes nodes layer by layer using a queue, which makes it especially efficient for keeping track of maximum values at each level. BFS is particularly intuitive for level order traversal, as it processes one row of nodes completely before moving on to the next. In implementing the iterative BFS approach, we start by initializing a queue with the root node of the tree. Then, for each level, we iterate through all nodes currently in the queue, tracking the largest value found at that level. Once we've processed all nodes in the current layer, we add their children to the queue for the next level. After determining the largest value for the current level, we store that value and proceed to the next layer of the tree. This process continues until all levels are traversed. The time complexity for this method is O(n), as we visit each node exactly once. The space complexity, however, is O, W, where W is the maximum width of the tree, as this is the largest number of nodes that the queue will need to hold at any given time. While this method is more memory efficient than recursive DFS for deep trees, it does require additional memory for maintaining the queue. Another alternative we considered was a divide and conquer approach. Here, we recursively compute the largest values for the left and right subtrees of the root, then combine the results to determine the largest values at each level. This strategy leverages the recursive nature of the binary tree structure, breaking the problem into smaller, independent subproblems. The time complexity remains O, n, as each node is visited once, and the space complexity is O, h, where h is the height of the tree. While elegant and conceptually appealing, this method does not offer significant advantages over BFS or DFS in the context of this problem. It also adds the complexity of combining results from the left and right subtrees, which can make the implementation less intuitive compared to BFS. The iterative BFS approach was ultimately chosen as the best solution for this problem. This method aligns perfectly with the requirement to process nodes level by level, making it a natural fit for computing the largest value in each row. Unlike the recursive DFS approach, BFS avoids the risk of stack overflow, which can occur in deep or skewed trees, and the queue-based implementation provides clear and efficient control over the traversal. The key insight is that BFS inherently processes nodes in a level-order fashion, allowing us to determine the largest value at each level incrementally without requiring multiple passes or additional complex data structures. Compared to DFS, BFS is more robust for trees with significant depth. And when compared to the divide and conquer approach, BFS is simpler to implement and avoids the overhead of combining results from subproblems. While BFS does require maintaining a queue proportional to the maximum width of the tree, this trade-off is generally acceptable as the width is naturally bounded by the number of nodes in the tree. Although DFS or divide and conquer might be preferable for certain types of problems, BFS's direct alignment with level-order traversal makes it the optimal choice here. With an efficient time complexity of O, n, and a space complexity of O, w, BFS is both robust and well-suited for solving this problem. Its iterative nature ensures reliability even for deep or skewed trees, and the simplicity of the approach makes it easy to understand and implement. This is why BFS stands out as the most effective strategy for determining the largest value in each row of a binary tree. In this problem, we need to identify the largest value in each row of a binary tree. To achieve this, we'll traverse the tree level by level and collect the maximum value from each row. This naturally leads us to use a breadth-first search, or BFS, approach. BFS is particularly suitable here because it processes the tree one level at a time, allowing us to compute the maximum value for each row as we traverse. To begin, we first check if the tree is empty. If it is, we simply return an empty list. Next, we initialize an empty list called result to store the maximum values of each row. We also create a queue, which we use to manage the nodes to be processed, starting with the root node of the tree. This queue will help maintain the correct order for level-by-level traversal. Once initialized, the algorithm proceeds to process the tree level by level, as we will see in more detail. At the start of processing a level, we determine how many nodes are currently in the queue. This number represents the size of the current level, which we call level_size. This ensures that we only process nodes that belong to the same row during this iteration. To track the largest value in the current row, we initialize a variable called max_value and set it to a very small number, such as -infinity. Then, for each node in the current level, we remove it from the queue and compare its value to the current max_value, updating max_value if the node's value is larger. After checking the node's value, we add its children to the queue if they exist. This prepares the algorithm to process the next level of the tree. Once all nodes in the current level have been processed, we append the max_value of that row to the result list. The process then repeats for subsequent levels until the queue is empty, ensuring that all rows in the tree are handled, and finally, the result list is returned. To illustrate this with an example, consider the binary tree shown here. It has 3 levels, and we'll process them one by one. At level 0, there's only the root node, 1, so the maximum value is 1. We then add its children, 3 and 2, to the queue. Moving to level 1, we process nodes 3 and 2. The maximum value in this level is 3, and we enqueue their children, 5, 3, and 9. At level 2, we process nodes 5, 3, and 9. Here, the maximum value is 9. After processing all levels, the final result is the list 1, 3, 9. This demonstrates how BFS ensures we process nodes level by level, calculating the maximum value for each row. The algorithm's efficiency stems from its systematic traversal of the tree and its ability to handle nodes in the correct order. By leveraging a queue, we ensure that all nodes are visited, and their children are added for subsequent processing. The time complexity is linear, O(n), since we visit each node exactly once, and the space complexity depends on the maximum width of the tree, which is typically O(n) in the worst case. The algorithm relies on two key data structures, a queue and a list. The queue is essential for managing the nodes during the level order traversal. Since it follows a first-in first-out order, it ensures that nodes are processed in the correct sequence, level by level. The list, on the other hand, is used to store the maximum values of each row, which will be returned as the final result. Additionally, it's important to consider edge cases that the algorithm handles gracefully. For instance, if the tree is empty, we return an empty list right away. If the tree contains only a single node, the result is a list with just the value of that node. The algorithm also naturally handles trees with uneven depths, since BFS processes nodes level by level regardless of the tree structure. To optimize further, initializing max_value to -infinity ensures that we avoid unnecessary comparisons, as the first node in a level will always update this value. Another optimization involves the use of a deque from Python's collections module. Deques allow for efficient enqueue and dequeue operations, each taking constant time, O(1). This ensures that the queue operations remain efficient even for large trees. Now let's look at the Python implementation. First, we import the deque class. The function begins by checking if the root is none. If it is, we return an empty list. We then create an empty list called result to store the maximum values and initialize the queue with the root node. The while loop runs as long as the queue is not empty. Inside the loop, we calculate the number of nodes in the current level using the queue's length, and we initialize max_value to -infinity. For each node in the level, we remove it from the queue, update max_value if necessary, and add its left and right children to the queue if they exist. After processing all nodes in the level, we append max_value to the result list. Finally, once all levels have been processed and the queue is empty, we return the result list, which contains the largest values from each row of the tree. This implementation is both efficient and easy to follow, leveraging BFS to ensure that all nodes are processed level by level. With its linear time complexity, O(n), and space complexity proportional to the maximum width of the tree, this solution is well suited for handling binary trees of various sizes and structures. By utilizing deques and carefully considering edge cases, the algorithm is robust and performs well across different scenarios. This Python code solves the problem of finding the largest value in each row of a binary tree using a breadth-first search (BFS) approach. Here's the step-by-step explanation of the code. 1. Importing the deque. The collections.deque is used to implement the BFS queue, as it provides efficient appending and popping from both ends. 2. Class definition. The solution class contains the method largest values, which performs the main logic for the problem. 3. Edge case handling. The function first checks if the root is none, empty tree. If it is, an empty list is immediately returned as there are no rows to process. 4. Queue initialization. A deque is initialized with the root node. This queue will help traverse the tree level by level. 5. Outer while loop. The while loop continues until the queue is empty, ensuring that all nodes in the tree are processed. 6. Level processing. The level_size variable determines the number of nodes in the current level. The max_value variable is initialized to -infinity to track the largest value in the current row. 7. Inner for loop. This loop iterates through all nodes in the current level. Each node is dequeued, and its value is compared with max_value to update the maximum value for the row. If the node has a left child, it is enqueued for processing in the next level. Similarly, if the node has a right child, it is enqueued. 8. Appending maximum value. After processing all nodes in the current level, max_value is appended to the result list. 9. Returning the result. Once all levels are processed and the queue is empty, the result list containing the largest values from each row is returned as the output. This BFS approach ensures that each level of the tree is processed completely before moving to the next, and it finds the maximum value for each level in O(n) time, where n is the number of nodes in the tree. The space complexity is O(w), where w is the maximum width of the tree, as the queue stores all nodes at the current level. Here, we start by importing the necessary libraries and defining the largest values method. This method takes the root of a binary tree as input and returns a list of the largest values in each tree row. First, we handle the edge case where the root is null by returning an empty list. After that, we initialize a result list to store the largest values and a queue to facilitate level order traversal of the tree. The root node is added to the queue to start the traversal. Now, we enter a while loop that continues as long as there are nodes in the queue. Inside the loop, we determine the number of nodes at the current level using queue.size, and initialize a variable max value to the smallest possible integer value. This ensures we can track the maximum value as we process each node at this level. Next, we use a for loop to iterate through all the nodes at the current level. For each node, we dequeue it from the queue, compare its value to max value to update the maximum, and add its left and right children to the queue if they exist. This prepares us to process the next level of the tree. After completing the iteration for a level, we add the max value for that level to the result list. The while loop then continues until all levels of the tree have been processed. Finally, we return the result list, which now contains the largest values from each row of the tree. Below the method, we also define a simple tree node class to represent the structure of each node in the binary tree. Each tree node has an integer value, a left child, and a right child. This class makes it easy to construct and interact with the binary tree. In summary, this implementation efficiently performs a level order traversal using a queue, ensuring that we capture the largest value at each level while maintaining a time complexity of O(n), where n is the number of nodes in the tree. Let's start with a basic binary tree example. The tree has 3 levels, with the root node having a value of 1. On the second level, the root has 2 children, a left child with value 3 and a right child with value 2. On the third level, the left child has 2 more children with values 5 and 3, while the right child has a single right child with value 9. To find the largest value in each row, we initialize an empty list, result, to store the largest values and a queue containing only the root node. Now, we process the first level. Since there is only one node in the queue, the level size is 1. We initialize max_value to -infinity. Dequeuing the root node, we compare its value with max_value and update max_value to 1. The root's children, nodes 3 and 2, are added to the queue. Finally, we append the largest value for this level, which is 1, to the result list. At this point, result becomes 1. Next, we process the second level, which contains 2 nodes, 3 and 2. The level size is 2, and we reset max_value to -infinity. First, we dequeue the node with value 3, compare its value with max_value, and update max_value to 3. This node has 2 children, 5 and 3, which are added to the queue. Then, we dequeue the node with value 2, compare its value with max_value, and find that max_value remains 3. This node has a single right child with value 9, which is also added to the queue. After processing this level, we append the largest value, 3, to the result list, making it 1, 3. Now for the third level. The queue contains 3 nodes with values 5, 3, and 9. The level size is 3, and we reset max_value to -infinity. First, we dequeue the node with value 5, compare it with max_value, and update max_value to 5. Next, we dequeue the node with value 3, compare it with max_value, and find that max_value stays 5. Finally, we dequeue the node with value 9, compare it with max_value, and update max_value to 9. We append 9 to the result list, which now becomes 1, 3, 9. This gives us the final output for this tree, 1, 3, 9. Now consider the second example, which is a single-node tree where the root has a value of 7. We initialize an empty list, result, and a queue containing only the root node. Since there is only one node, the level size is 1, and we reset max_value to -infinity. Dequeuing the root node, we compare its value with max_value and update max_value to 7. We append 7 to the result list, resulting in 7. This is the final output for the single-node tree. Finally, in the case of an empty tree where the root is none, there are no nodes to process. We simply return an empty list as the result, which is. These examples demonstrate how the algorithm works in different scenarios, from basic trees to edge cases like single-node or empty trees. To evaluate the time complexity of this algorithm, we consider its use of a breadth-first search, or BFS, traversal. The algorithm processes each node in the binary tree exactly once. This means that for a tree with n nodes, the work involved in visiting all nodes amounts to O(n). Additionally, the algorithm performs operations for all nodes at each level of the tree. If the tree has h levels, the sum of nodes across all levels is still n, so the per-level iteration also contributes O(n) overall. Lastly, constant time operations, such as finding the maximum value at each level, adding children to the queue, and performing comparisons, are O(1) per node. Combining these components, the overall time complexity of the algorithm is O(n), as the work performed is proportional to the number of nodes in the tree. Now let's analyze the space complexity, which primarily depends on the memory used by the queue and the result list. The queue holds nodes from a single level of the tree at any given time. The maximum number of nodes at one level corresponds to the width of the tree. In the worst-case scenario, such as in a perfectly balanced binary tree, the width can be up to n/2, leading to an O(n) space requirement for the queue. For skewed trees, where only one node exists per level, the queue size reduces to O(1). The result list, on the other hand, stores one entry per tree level, which corresponds to the height h of the tree. In a worst-case scenario, the height of the tree is O(n) for skewed trees, while in balanced trees, it is O log n. Therefore, the space complexity is dominated by the queue in wide trees, resulting in O(n) in the worst case. For balanced trees, the space complexity improves to O log n, as the height is smaller. When comparing approaches, a naive solution would involve traversing the tree level by level while storing all node values at each level in a temporary list before computing the maximum. This approach increases memory usage significantly because it requires extra space for the temporary list at each level. By contrast, the BFS algorithm we've implemented avoids this inefficiency by calculating the maximum value directly during traversal, reducing memory usage. Another potential solution is using a recursive depth-first search, or DFS, which also processes nodes efficiently. However, DFS requires stack space proportional to the height of the tree, O(h), which is equivalent to the space used by the BFS queue. Ultimately, the BFS algorithm is optimal for this problem, achieving O(n) time complexity since each node is visited exactly once, and maintaining balanced space efficiency. In the worst case, space complexity is O(n) for wide trees, while for balanced trees it improves to O log n due to reduced height. When working on this problem, there are a few common mistakes to watch out for. First, not handling empty trees is a frequent oversight. If the input binary tree is empty, you must ensure your code returns an empty list, rather than an uninitialized variable or none. Next, if you're using a DFS approach, tracking the depth incorrectly can lead to values being assigned to the wrong level. To avoid this, make sure the depth is properly passed as a parameter and used consistently to index your result list. Inefficient traversal is another pitfall. Traversing the tree multiple times to find the maximum value for each level results in unnecessary computations, increasing time complexity to O(h*n). Instead, aim to traverse the tree just once while calculating the maximum values simultaneously. Lastly, don't overlook edge cases. Trees with only one node, highly unbalanced trees, or even nodes with negative values can introduce subtle bugs. Thorough testing with these scenarios is key to building a robust solution. Another mistake to consider is using excessive space. For example, creating redundant copies of lists or introducing additional data structures unnecessarily can inflate your solution's space complexity. To optimize, focus on using only the essential data structures required for the task. From an interview perspective, this problem is a great opportunity to demonstrate pattern recognition. It's a textbook example of level order traversal, so recognizing this upfront allows you to quickly decide between BFS or DFS as your approach. Be prepared to discuss the trade-offs. While BFS is typically more intuitive for level-based problems, DFS can sometimes be more memory efficient. Additionally, optimization is key. Think about minimizing both time and space complexity, such as avoiding intermediate results that don't contribute directly to the solution. Finally, communication matters. Clearly explain your thought process to the interviewer, especially how you're addressing edge cases and why you chose one traversal method over the other. This shows both technical and problem-solving skills. This problem is also linked to several related LeetCode problems, which can help you deepen your understanding of tree traversal techniques. For instance, LeetCode 102 focuses on basic binary tree level order traversal, while LeetCode 107 adds a twist by reversing the level order. LeetCode 103 introduces zigzag traversal, and LeetCode 199 focuses on the binary tree's right-side view. Exploring these problems can give you a broader perspective on level-wise tree processing. As for alternative approaches, the BFS method uses a queue to perform level order traversal, and during the traversal, you calculate the maximum value for each level. This has a time complexity of O(n), where n is the number of nodes, and a space complexity of O(w), where w is the maximum width of the tree. BFS is straightforward to implement, but its use of a queue means additional space is required. On the other hand, the DFS approach uses recursion to traverse the tree. Here, you maintain a list to store the maximum value for each level. It also has a time complexity of O(n), but its space complexity is O(h), where h is the height of the tree. DFS can be more memory efficient for shallow trees, but it requires careful management of depth to avoid errors. There's also a hybrid approach that combines ideas from both BFS and DFS. In this method, you use an iterative stack-based DFS while maintaining level-wise information, similar to what BFS would track. This can be particularly useful when you're working under strict memory constraints and need an alternative to recursion or queues. By blending the strengths of both strategies, the hybrid approach offers flexibility in handling a variety of tree structures while maintaining efficiency. It's an excellent option to consider when optimizing for both time and space in scenarios where traditional methods fall short. Great work! To recap, we solved the problem of finding the largest value in each row of a binary tree. We discussed efficient approaches, highlighted key concepts, and learned when to apply specific techniques. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!